All right, so yesterday we talked about where the equation for a trapezoid came from, and of course how to use it. We very quickly, we said what the equation of a kite and a rhombus is, but I didn't get a chance to show you where it comes from, so I'll do that real quick here. I'm going to take a look at a kite. That is not my best ever kite. Let's see if I can do it a little better for presentation purposes. Much better. All right, so we have a kite, and I want to derive the equation of a kite by looking at two triangles. This blue triangle and this red triangle. Okay? So looking at those two triangles, I then know that my area is going to be triangle plus triangle, which will be 1/2 base times height plus 1/2 base times height. Okay. First things first, let's take a look at the blue triangle there on the right. I'll zoom in here a little bit. The blue triangle on the right, I'm going to call this segment here my base. And the reason I'm doing that is because I know the diagonals of a kite are perpendicular to each other. So therefore, I know that this can be my height. All right? So I have my base here, and I have my height there. But if we look at it in terms of the kite rather than the triangle, the base is actually one of the diagonals. So let's call that diagonal 1. The height is then part of the second diagonal, correct? But remember, one of the properties of a kite is that the vertex diagonal bisects the non-vertex diagonal. And so therefore, this is actually half of diagonal 2. Right? Which makes this the other half of diagonal 2. So, if we're now looking at our equation, in the blue triangle, my equation is 1/2 times the base, which we said was diagonal 1, times the height, which we said was half of diagonal 2. I want to do the same thing for the red triangle. 1/2 base times height. My base is still diagonal 1. They share that side in the two triangles. My height is then the other half of diagonal 2. So I have some multiplying I can do. 1/2 times 1/2 is 1/4. Diagonal 1 times diagonal 2. Plus again, 1/2 times 1/2 is 1/4. Diagonal 1 times diagonal 2. Those are like terms. They have the same variables. D sub 1, D sub 2. So what is 1/2 plus 1/2? I'm sorry, 1/4 plus 1/4. 2/4, which reduces to 1/2. And so by starting with shapes that we knew how to find the area of triangles. We knew the formula for the area of triangles. We were able to then derive the equation for a kite. Now, because a kite shares the same properties of its diagonals as a rhombus, meaning a rhombus, the diagonals bisect each other, and the diagonals of a rhombus are perpendicular to each other. Therefore, we're able to use the same equation for a rhombus. Okay, because the exact same deriving the formula I did here works for a rhombus as well. But something else to remember about a rhombus. In a rhombus, depending on what information is given to you, you can actually use or find the area of a rhombus two different ways. You could use the diagonals and say your area is 1/2 d sub 1 times d sub 2. But remember, a rhombus is also a parallelogram. And so again, depending on the information they give you, you might simply want to treat the rhombus as a parallelogram and say its area is base times height. Okay, so for a rhombus, you have two options. It all depends on what dimensions they give you as far as which approach you want to take. Okay? Questions on those two equations? Or two shapes, I should say. It's actually only one equation. Good to go? Then, taking a look here, let's go down to the last example. Oops. The last example here on the page. I know on your page it's kind of hard to see that it's there, and actually on the screen it's a little difficult to see as well. But we have red lines here, which are our diagonals being drawn in there. Okay, they're hard to see, but they're there, trust me. Okay, they give us the length of AC, they give us the length of CB. We want to find the area of this. This is actually going to be, they call them diamonds in the road, obviously, but it's a rhombus. Okay? And by the way, I don't know if you guys knew this or not, but there's really no geometric shape called a diamond. It's a rhombus. Okay? It's a rhombus, or it's a square. Or it's things that we call diamonds are actually other shapes in geometry. And the only reason I bring that up is because they call it here, and my son is 4, and he's learning his shapes. And they're preschool, they call it diamonds. And I cringe, but then I remind myself he's 4. He can call it a diamond if he wants. I'll teach him better when he's older. All right, so here we go. Looking at this shape, first off, what approach do you think we should take? Should we try to do this as a parallelogram, base times height? Or should we try to do this as the other formula for a rhombus, 1/2 d1 times d2? The second formula, right? That's what you mean. Yeah, absolutely, because they give us diagonals here. So area equals 1/2 d sub 1 times d sub 2. And what we're going to do, if we look closer in here, we want to focus on one triangle. Let's see. Let's focus on that one. Because I'm focusing on that one, of course, because I know 2 of its sides, right? So I can go ahead and find my missing side, my third side here, I'll call it x, by doing what? Pythagorean Theorem, absolutely. So we know that a squared plus b squared equals c squared, therefore x squared plus 2.5 squared equals 6.5 squared. So x squared is going to equal 6.5 squared minus 2.5 squared. And I can grab my calculator. So we have 6.5 squared. That is 42.25. And 2.5 squared is 6.25. And so we are going to end up getting 42 minus 6 is 36. So we got to take the square root of both sides. X equals 6. So if that side is 6, again, we're dealing with a rhombus here, and we know the diagonals of a rhombus bisect each other. So that means our entire long diagonal, the vertical one, is going to be how long? Yeah, 12 feet. Area is going to equal 1/2 times 12. And then the horizontal diagonal is going to be how long? 5 feet. 1/2 times 12 is 6. 6 times 5 is 30 square feet.